Hello everybody and welcome to this Umehluko Grade 12 Physical Sciences Revision lesson. Today we are going to start the topic of the Doppler effect. If you see, the Doppler effect is defined as the change in the observed frequency of a wave when the source or the detector are in relative motion. So imagine you are standing beside the road, and I'm not sure how many of you have had this experience, but there's the road, you standing beside the road and just minding your own business, and suddenly here comes an ambulance racing along. Someone's in trouble, someone's on the way to the hospital, sirens are blaring, the lights are flashing, and this ambulance is making a sound. And when you stand, as the ambulance comes towards you, the pitch of the sound increases, so the frequency of the siren becomes higher, and as it passes you, the frequency becomes lower. And that is called the Doppler effect. So how does this work? This works because either you are standing still and the ambulance is moving towards you, or the ambulance is standing still and you are moving towards it. Another case which we will not consider is when both the ambulance and the observer are moving at the same time. So if we consider this example, and what we can do is we can visualize the sound waves as circular waves. So if we look at this, let's just assume to begin with that the ambulance is standing still. Ambulance is standing still, that will be this position here. It's going to be, the light's going to come out, and then the waves, the sound waves, are going to flow from the siren. And so these sound waves spread out in all directions. We consider them to be circular waves. And what we can then do is we can look at what these sound waves look like when the source, in this case the ambulance, is stationary. What we can do is if we draw the waves, you'll notice that the waves will go and they look something like this. And the spacing between the peaks and the troughs of the waves will be the same. The distance between the waves will be the same. Now, in waves, we have an equation called the wave equation, and we can say that the speed of a wave is equal to the frequency of the wave multiplied by the wavelength of the wave. V equals F lambda. So this is the speed, this is the frequency, and this is the wavelength. So to understand the Doppler effect, we need to understand the concepts of waves that we have studied in the past. Another idea here is also, so the frequency is the number of oscillations per second. The wavelength is the distance between two consecutive peaks or troughs in the wave. Right? If the wave, we look from the side, this is the sine wave. Then the distance between that peak and that peak, that is called the wavelength. The other concept that we are interested in understanding is that of the period. T is the period, which is 1 over the frequency, and that is the time for one oscillation. So these are all very important concepts, and we will use them in our discussion of the Doppler effect. All right, so what this means, once again, if we had a stationary observer standing over here, and the ambulance is sending out its waves, then if they're both stationary, the wavelength remains the same, the number of oscillations remains the same, the frequency of the sound remains the same. Now, we want to see what happens in the case of a moving object. What if the source moves? What do the waves look like with a moving source? And there are two different cases. The case of when the movement is towards the observer, and the case of movement away from the observer. Right, in both of these cases, something different is going to happen. So let's first consider the movement which is towards the observer. So there's the ground, there's the observer, and here's the object moving, and I'm just going to make it as a point object, and the object is moving towards the observer. So what will happen is that these waves, so if we have the waves, this is the first wave, right? When the object that makes the sound, the siren of the ambulance in this case, this is going to be the wave that we'll have in the first position. And this wave is going to travel out. Remember that these wave fronts, they travel along, so as time goes by, they will spread out. And we'll show that as a dotted line as the wave front spreading out. All right. So as the wave front spreads out, that is going to have an effect on the frequency, because what's going to happen is as the object moves towards the observer, it's going to seem as if the wave fronts are going to be piled up on each other. In other words, they will be closer and closer together. Everything else being the same wavelength, same amplitude, in other words, they're equally loud, the wave fronts, we will see what happens to the wave fronts. So what's going to happen to the wave front is something like this. As the object moves, we're going to, this is the initial position. What's now happened is, after a little while, the object is now closer to the observer. And what's happened is that the wave fronts will form a shape like this. Because these wave fronts keep moving, they are going to pile up in front of the object making the sound, and so to the stationary observer, this wavelength is going to be smaller. The wavelength that the observer hears will be a shorter wavelength. So if we look at the wave equation, V equals F lambda, the speed of the waves will be the same. This is the speed of sound in air. It's about 340 meters per second. So the speed will remain constant. What is going to happen is, when you look at this, you'll see that the wavelength is going to decrease. So the wavelength will decrease. But the speed must remain constant. So if the wavelength decreases, what is going to have to happen to the frequency? If we look at the frequency term in our wave equation, well, the frequency will have to change to cancel out the change in the wavelength. And so what's going to happen with that is that the frequency is going to get bigger to be able to counteract the change in the wavelength. So these two things will cancel each other, will work against each other to keep the speed of the wave the same. All right, and then this increase in frequency corresponds to the increase in pitch that is heard by the observer as the object approaches. And so what we want to do is we want to then see what the opposite situation is. And if we look at the opposite system, what we've got is, if we have a level ground there, we have our observer on the one side, and now our object is moving away from the observer. What will happen is that it will seem as if the waves are stretching out towards the observer. The wavelength will seem to increase as you go towards the observer. And because of this, it will then be matched by a decrease in the frequency, and therefore as the object moves away, you will have a decrease in the frequency. The pitch of the sound will lower as the object moves away. And we're able to then use this, and we can work out a equation for the relative velocities of the source, of the observer, and in terms of the frequencies of the sound. And that's what we will consider next. Okay. So, if we do this, we can do some worked examples for this, and let's look at what this looks like. So what we're able to do is we can derive a formula that shows the relationship between the frequency emitted by the source and the frequency measured by the listener. And that equation is as follows. The frequency observed by the listener or the observer is going to be equal to some modification of the frequency that is emitted by the source. And this is going to be given by the following equation. Right. So what this is this is the frequency observed by the listener. This is the frequency of the source. This V, this is just the speed of sound. The normal speed of sound with if we had a stationary object emitting the frequency, right? And then what we have here, Vs, this is the speed of the source. Moving object will have a certain speed, and that is going to affect the frequency that is heard by the listener. And this here, VL, this is the speed of the listener. Right, so we've got the frequency, the speed of sound, the speed of the listener, and the speed of the source. Now, we have to use this, and what we have to do is we've got to consider what happens when the movement is relative to each other. So is the listener moving towards the source? Is the listener moving away from the source? Is the what is the relative motion between the source? And so this is summarized by the following. So very importantly, let's write this down. So first, if the source moves towards the listener, right? In this case, the velocity of the source is going to be negative. If the source moves away from the listener, the velocity is going to be positive. Right? So depending on what the relative motion is, we have to substitute the correct sign for the velocity into the equation given here. And then also, if we move about the sound, the listener, so if the listener moves towards the source, then VL is positive. And if the listener moves away from the source, then VL is going to be negative. Right. So what we will do, we'll only look at either the source or the listener moving in this case. So we won't consider both of them. So consider only either the source or the listener moving. And for us to do that, let's look at some example. Right, so here is our example. We're going to consider an ambulance. Right, so what we've got is that an ambulance siren emits a sound at a frequency of 700 hertz. Remember that the unit of frequency is hertz. Right. The ambulance drives past you as a stationary observer at a speed of 20 meters per second. Right. So the question is the following. What frequency will you hear? Right? First, as the ambulance approaches you, and secondly, as the ambulance moves away from you. Right. For this, we're going to need the speed of sound in air. So remember, that's the V in that equation there. Let V equal to 340 meters per second, right, for the sound in the air. Okay, so now we can do the calculation. Right, we know that this is a Doppler effect question because we have a relative motion of the producer of the sound and of the listener. All right, so let's look at our equation. Our equation is given by FL equals V plus or minus VL divided by V plus or minus Vs times the frequency of the source. So this is all, just to be clear, this is all within the bracket. Right. So let's write down the information that we've got. So we know that the ambulance, which is the source, has a sound that is a frequency of 700 Hertz. We are going to look at the speed of sound in air, which is 340 meters per second. You are the listener, but you are stationary, so your velocity is going to be equal to 0 meters per second. And for the first case, the velocity of the source is going to be minus 20 meters per second. Right? Why is it minus 20 meters per second? Because if we look at our information on the previous page, if the source is moving towards the listener, the velocity of the source is negative. And so because it's moving towards, it's going to be negative. And the second part of the question talks about the source away from the listener. So in that case, the velocity of the source, which is the siren, is going to be positive. So let's first look at this, and then we'll just make a note here. For the second case, Vs is going to be 20 meters per second. Right. So now, what we want to do is we are going to do the calculation. Right. So first of all, we want to find the frequency that you are going to hear by using this equation. So we'll see f of L. We've got the equation there, so let's substitute the values in that we've got. So the the velocity of the sound is 340, right? And then you are stationary, so your velocity is 0. For the siren of the ambulance, it's going to be 340, and in this case, the answer is going to be negative. So this will be minus 20 meters per second. So that will include there. Source is coming towards you, so Vs is negative. And if we work this out, we'll get an answer of 743.75 Hertz. Right. So this is for the first case. For the second case, we do the same thing. What is the frequency that you are going to hear when the siren moves away from you? You're still stationary, so it's still the speed of sound plus or minus 0. Now it's going to be 340 plus 20 times 700, and that will give us a frequency of 661.11 Hertz. In other words, we see that the frequency has decreased because it's moving away from you. And this is exactly what we would expect. So this is very important to understand. If we look at a question like this plus or minus here depends on whether the relative motion is regarding with respect to the observer and the source. Thank you very much. We'll see you next time.